Hello everyone and welcome to your week 4 lecture. This week we'll be looking at linking between exposure and diseases via chance and biases. So I'll explain further what this means. So basically today's lecture will be focusing on two main points, which is what is chance and what is bias, which is random error and systematic error. All right, and what are the real life implications of this? This is very important, guys, particularly to understand research articles, because this will help you to critique research articles better, meaning what the author has reported. Do you deem that there could be plausibility of type 1 error, type 2 error? Do they have a strong methodological foundation, analytical foundation to, say, avoid biases? Or are they result simply by chance? So these kind of things you get to know better once you know the basic concepts of random error and systematic error. All right, so guys, although the different type of sampling methods, this is more of a research methods topic, but I just wanted to share these videos with you. So this does not come into epidemiology, but this sits well into, say, if you had a unit such as research methods, this is where you would learn various types of sampling methods. All right, so this is just an FYI video. It is not really connected to what we will be studying throughout the lecture, but this is good for you to know in case if you're taking up higher research degree as one of your, say, potential future careers. All right. Okay, so yes, as I said that today we are going to understand what links exposure and outcomes. So as I have given very simple example throughout these lectures, your exposure over here could be, say, smoking, which is your independent variable, and your outcome could be, say, cancer, which is your dependent variable. All right, so before we claim causations, as I said, like, it's not wise to use, say, causations or state that this is a causal relationship before investigating the facts. All right. If you remember lecture 1, you guys are, say, detectives. All right. You are scientific detectives, epidemiology. That is what it is all about. So basically, before claiming causations, you need to identify whether the association between smoking and cancer, could it be because of a random error or a systematic error or confounders? So confounders is something which is going to be covered in week 5. But today what we are going to look at is chance and biases, right? So we'll first start with chance or random error. So basically, what is chance or random sampling error? So what it means is that to identify that the association which you have between, say, smoking and cancer, is this really what is happening in the wider population? So in your sample of, say, 50 adults, you may have found that there is an association between smoking and cancer. But is this representative of all adults who are living in Canberra, for example? Okay, meaning, is this result applicable, or is this result what is a true reflection of the wider population? All right, and because why? If not, the association that you may have found in your little sample of 50 adults, this could be just a luck or chance, or in scientific terms called as random sampling error. So basically, chance is something like luck, that you're lucky you found an association, but hang on, this is not the association which is reflective of the wider population. All right, so this is what we mean, or this is what the concept is about random sampling error. Okay, so yes, the second thing is, why are we sampling in the first place? Because it's very logical that you cannot study the entire population. So you cannot study every adult in Australia, all right? And that's why you take a sample of the population and you try to investigate your research question within that sample, all right? And therefore, the pre-reading which I gave you regarding, say, various types of sampling method, that becomes very important for you to identify which is the most appropriate type of sampling method. Now, guys, what it is important to understand that you may have the most ideal sampling method, say, which is, say, random sampling methods, but sometimes because of practical difficulties and limitations, you may not be able to apply the most idealistic sampling method to your research study. All right, especially when you are piloting a new research program or your new research question, you may just the most practical and the feasible thing for you in terms of time, cost, labor, etc., deadlines which you have as a student, you may be considering that convenience or snowball sampling method is the most say suitable method for me, because I have to do quick, I have to be fast, I have limited funds, and you may not be able to do a more idealistic approach, which is say random sampling technique. All right, so this is where I wanted to show you those YouTube videos, because when I refer to sampling in this lecture, you have some idea, but ideally if you are taking a subject such as research methods, which is something which students are meant to take before they start a higher research education degree, then you will be learning more about sampling techniques. Okay, but just as an FYI, firstly, why do you sample? Is because you cannot study the entire population. Which sampling method you choose, that depends upon a lot of pragmatic factors which are applicable for your research. Yes, it is good to know which are the best sampling methods or the most idealistic sampling methods, but sometimes you may end up doing something which is based on of convenience, like a snowball sampling technique, only because that's the most practical thing which you can do. All right, so for example, the study which I'm doing, and don't mind guys, I keep on sharing with you a lot of these examples of my previous research, current research, just so that it makes everything makes more, say, it sounds more realistic to you, that okay, yeah, this is how it's applied in real life. All right, so for example, the picky eating study which I'm doing, looking at the genetic factors and the environmental factors. So this is a pilot study which I'm doing. Pilot study meaning a study which is done for the very first time, which is looking at both of these factors, genetic and environment, in one study. All right, so because this is a pilot program, a pilot study, and I'm doing it across countries, right? So I'm doing it in Australia, my colleagues are doing it in Malaysia. So this is a big multi-centric study. All of us are piloting it. So we are taking the most simplistic sampling method approach, which is called as convenience-based sampling or snowball sampling. All right. So yes, this may increase our risk of, say, type 1 error, but then you take into consideration a lot of other, say, if you consider a lot of other factors, and if you're doing it robustly, such as your methodological techniques, such as your questionnaire data collection, if it is done in a more robust manner, then you minimize the chances of your type 1 error. So basically, guys, what am I trying to say? At the end, in research, you cannot nullify type 1 or type 2 error, or say random sampling error or systematic error, which we will be learning in the coming slides. You minimize errors. All right, so you cannot get rid of all and every error, but you can minimize errors. All right, so that is the concept you need to keep in mind, that what are the errors which we can minimize. Okay, all right. So yes, so even if you the third point over here is, even if you study, yes, this is very important guys, even if you study, say, several different samples from the same population. Okay, so you have, say, Australian adults, as I said, all right, who are smoking, and you want to see the risk of cancer. All right, so even if you take several adult population, which is, say, 1 from Canberra, or say maybe 2 from Canberra, 3 from Melbourne, 5 from Sydney. All right, so you take different populations from different samples from the same population, which is the Australian adult population. It is very highly likely that you will find slightly different result in each of your sample population. All right, so sample 1 may show, I'll just hover my mouse over there. Sample 1 may show a strong association, meaning there is a very strong association between smoking and cancer. Now I say, when there is a very strong association, when you look at your weak force tutorial, everything will make more sense to you. You will be able to connect the dots better. Because when I talk about strong association, it could be, say, such as Pearson's correlation with a very big R value. Okay, and I talk more about this in a tutorial, and it will be in the coming slides as well. All right. So in sample 2, you may find a moderate association. In sample 3, which could be from Sydney, you may find a very weak association. In sample 4, which could be from Melbourne, you may find no association, meaning there is no association between smoking and cancer. Okay. So why are there these differences in result? Although it is coming from the same population, which is the Australian adult population. This is because you are studying people, you are studying human beings, okay? You are studying different type of people in your different type of samples, okay? And different type of people have different lifestyle choices, behavioral choices, dietary choices, occupation, a lot of variables which may influence the final result, which is the association between smoking and cancer, okay? So that is what is called as random sampling error, okay? So meaning when you have a lot of variables which may influence your two key variables, which is smoking and cancer, this could be called as random sampling error. Now, random sampling error, which I briefly spoke about, can lead to type 1 and type 2 error. Okay, so now what are these type 1 and type 2 error? We'll look at it in this box. So over here you have the columns. Okay, so I'm referring to the columns. It's the truth, meaning based on the entire population. Okay, so what is really happening in the population? All right. So what is really happening in the population over here, it says nothing is there. All right, meaning there is no association between smoking and cancer, meaning people who are smoking, it's not that all of them get cancer, or there is no strong, weak or association, moderate association, there is just no association. All right, so the population shows that there is no association between smoking and cancer. All right, and you have taken a sample of this Australian population. Okay, you could be doing a pilot study, you could be a uni student, you could be just doing it within, say, adult university students who are going to University of Canberra. All right, so a very, very specific targeted population. And what you see is, yes, that even in your sample, there is no association between smoking and cancer. So basically, this is right. The population is telling you there is no association between smoking and cancer. Your sample results, your sample, okay, within your sample, the results are showing that yes, there is no association between smoking and cancer. So both of you are right. Your sample is right, and that is reflective of the larger population. All right. And you would say, where is this larger population data coming from? Think of it as the national data set. Okay, Australian Bureau of Statistics national data set. You know from that how many people are smoking. You know from that how many people have cancer. And you may have done a bivariate analysis between smoking and cancer. This is called as an ecological study, if you remember from your lecture 2. All right, so you look at the very, very big, large national data set, and this is what it says, that no, there is no association between smoking and cancer. Then you may choose to do, say, a smaller study, say within the university students in Canberra, and you find the same thing. Okay, so your findings are aligning with the population findings. All right, then what may happen, that the population says that no, there is nothing there. All right, there is no association between smoking and cancer. All right, but you see there is something significant. All right, meaning you see that yes, there is an association between smoking and cancer. Now guys, over here, when is it a type 1 error? When you generalize, okay, when you interpret your finding as, look, in the students that we surveyed, adult students that we surveyed in University of Canberra, we found that there is an association between smoking and cancer, meaning this is reflective of the larger Australian population. No, this is what I'm saying. That is type 1 error, when you're overgeneralizing your results, when you're overstating your results. Okay, so I hope you understand the point. When is it a type 1 error? When you are, say, generalizing your findings to the wider population, whereas you really haven't. This population which you're studying is not representative of the wider population. You're just studying university students who are going to Canberra. This does not reflect the Australian adult population. Okay, now within this tiny population, if you see these results, not that you should be ignoring it. Probably it is that you need to design a you need to design an intervention which is systematically catered particularly to the university students. All right, so yes, that could be beneficial definitely for your sample population in the long run, but you cannot say this is what we have seen and this is what is happening all over Australia. No, that is type 1 error. Does that make sense? All right. Okay. Now, where is type 2 error? So in type 2 error, you the population says, yes, there is something. There is a association between smoking and cancer. So the national data set is telling you, yes, there is an association between smoking and cancer. Okay. And in your tiny sample population, what you saw is that there is no association. I don't see. Okay. So there is no association between smoking and cancer. All right. So, okay, it is fine. It is absolutely fine for you not to find an association. But then over here, basically, if you read a research paper, you have a limitation section. That is where the authors, they would generally acknowledge that, look, for us, our sample population is only pertaining to the university students within the University of Canberra. And it could be that the 80% of your sample within these university students within University of Canberra, they are studying health science courses, meaning they are more aware about, say, the detrimental effect of smoking on health, physiology, well-being, and stuff like that. And so maybe these students are more aware, they are more mindful, they are more, say, educated about the harmful effects of smoking, and therefore they choose not to smoke. Okay. So only because you say, because you saw that there is no association between smoking and cancer between these students, even if they were smoking, all right, or maybe they had a very fantastic good lifestyle, lot of exercise, lot of diet, and they are young also. So maybe a lot of variables because of which you did not see an association. Now, you cannot generalize this result to all of the university students within the University of Canberra, all of the university students beyond your University of Canberra, meaning within the entire Australian setting or the Australian adult general population. Okay, if you do so, then that is called as a type 2 error. Okay, so again, this is what type 2 error is, where the population shows that there is an association. You may not see a significant effect. And again, why you may not see a significant effect? As I said, there are many, many reasons. There could be multiple variables. They had a very healthy lifestyle, good exercise, cardio, weights. They are young, and maybe your sample size was really tiny. You just like surveyed what, say maybe 25 to 30 students. And you did not have enough power to actually like generalize your results to the wider population. So not enough power to detect significance as well. All right. So yes, that's why you did not see any findings, significant findings. And within that, you are at higher risk of type 2 error. If you say this is what is representative of the wider population, no, then you have to acknowledge your limitation. That look, our sample size was tiny, and that's why maybe we did not have sufficient power to detect a significant result. Also, there could be various other variables as to why we could not find an association: diet, lifestyle, age, stuff like that. All right. And what if the wider population shows that yes, there is an association between smoking and cancer, and you also find that there is an association between smoking and cancer? So yes, that is when you do not have, say, a type 2 error. But again, guys, over here in real life, you still need to acknowledge the factors which could be influencing your sample. So acknowledgement needs to be done irrespective of the case, meaning you still need to acknowledge, yes, we saw a significant result. In our sample, smoking was associated with cancer, but we have to be mindful that our sample size was very, very tiny. Okay. And maybe this is not representative of the wider population, meaning the wider Australian population of university students or adult population. You still need to basically, you're saying that future research needs to do this study inclusive of a wider population where the sample is systematically sampled, all right, for them to find consistent and reliable findings. Okay. So this is what it means. All right. Type 1 and type 2 error. I hope this makes sense. Okay. So always remember, type 1 error is when the population says there is no association, but you see an association in your result. Type 1 error. Type 2 error, when the population says there is an association, but you see that there is no association. Okay. So that is type 2 error, when you don't see an association. Yep. So I just wanted to make sure that I'm pointing towards the right things. Okay. So yes, so this is your type 1 and type 2 error. All right. So basically, random sampling error can lead to type 1 and type 2 error. So it depends a lot. So one of the first things which you do in your research is, when you start collecting data, who do you start collecting data on? A sample of the entire population. And therefore, a sampling technique is so very much important to be considered while designing a research study. Okay. So now moving forward, how do you minimize the random sampling error, okay, or type 1 and type 2 error, all right? So basically you undertake hypothesis testing, all right? So in simple terms, it says that you are innocent until you're proven guilty, all right? So your null hypothesis, which is H naught, okay? So your null hypothesis is, you start off saying there is no association between smoking and cancer in your sample of those 30 adults or 50 adults which you have, okay? So yes, you start off saying that there is no association between smoking and cancer, okay, meaning you are innocent, all right? So the alternate hypothesis is that there is a association between smoking and cancer, meaning you are guilty, okay, in simple terms. And in this case, you reject the null hypothesis. Hypothesis proving means that you may develop a hypothesis. So where do you generally write this hypothesis? You do a literature review search. So I'll explain it to you in form of, say, real life practice as to how do you write this, okay? So you have a manuscript, you're writing a research paper. You review the literature. In the literature, you see that national data set of Australia, national data set of UK, globally, they are showing a very strong trend, meaning international and national data set are telling you that individuals who smoke, they are more likely to suffer from cancer risk, okay? Then you also, in your literature review, look at other original articles, okay? If you don't know what original article is, week 2 lecture, all right? You look at several original articles, all right? You also look at systematic reviews and meta-analysis. And a lot of these individual research, individual studies, and say group of studies as systematic reviews and meta-analysis are also telling you the same trend, meaning yes, individuals who are smoking, they are likely to be suffering from a risk of cancer, okay? So now over here at the end, you make a hypothesis, all right? You say the literature has shown that the probability of individuals smoking and suffering from cancer is high. And we assume, we hypothesize that we may be seeing these similar results within our sampled of population, which is university students attending University of Canberra. All right, so makes sense. So this is how you formulate the hypothesis. You look at the wider literature, international, national data sets, original articles, systematic review, meta-analysis. What is the trend? What is the story? Is there a pattern in the existing literature? Based on that, it gives you sufficient evidence to form a hypothesis, all right? And then you form a hypothesis, and then you see whether the hypothesis is true or false in your sample, okay? Meaning, is there an association between smoking and cancer? In this case, you reject the null hypothesis, which is that there is no association between smoking and cancer, all right? So the first way of minimizing, as I said, you can only minimize things. It's not that you will never have type 1 and type 2 error. That's not practical and feasible. You're studying humans. As I said, there is a lot of variation. Okay, so you minimize type 1 and type 2 error. All right, the first thing which you do is you formulate hypothesis. How are hypotheses formulated? Most of the time they are formulated based on existing evidence, okay, which tells you a story, which tells you a pattern. All right. So this is where you see this in manuscripts, okay, when you read research papers. All right, then how do you correctly accept or reject hypothesis? Okay, so basically you undertake statistical test. Now you have a hypothesis. After you have read the literature, you say that the literature says association between smoking and cancer. We hypothesize that in our sample, we will have an association between smoking and cancer. Okay, then you collect your data. Okay, you may have done a, say, convenience-based sampling technique, because that's the only thing which you could afford as a uni student, and time, money, labor, all of that, which is okay. You will acknowledge this limitation in your limitation section. Okay, now what do? You have to prove this hypothesis. Now, when we say proving a hypothesis, meaning you have to conduct specific type of statistical test. And I talk a lot about statistical test, guys, in your week 4 tutorial video, okay? Bivariate test versus multivariate test. So I won't go into details of that, but it will all make sense when you see this and you see the tutorial video throughout, okay? So yes, so basically over here, the take home message is that you accept or reject a hypothesis based upon your statistical test. Okay, so you do a statistical test, okay, not just a test, you may do a lot of testing, all right? And then the p-values which you get, the effect size which you get, and if you have sufficient power, this will help you to minimize your type 1 and type 2 error or your random sampling error. Okay, so there are three key factors which we will be looking at in detail in the coming slides, which is p-values, effect size, and power of your sample. This will help you to minimize type 1 and type 2 error. Okay. So the first thing is, how do you minimize type 1 error? All right. And we are looking at p-values. Okay, over here. So the way to minimize type 1 error is to accurately interpret p-values. So what does p-value mean? Let us look at that. So your significance, okay, when you say your result are significant, so what does significant means? It means p-values which are less than 0.05, okay? What does this 0.05 mean? It means that there is a 95% confirmation or confidence that your results are accurate, and they are not because of chance or not because you are just simply lucky. Okay, so your statistical tests are designed in such a way in which you can have 95% confidence that if I see a association between smoking and cancer in my sampled results, meaning this is 95% accurate. Okay, there is always 5% chance of error. That is how statistic is. Okay, it is not 100% ever. All right, and now you would appreciate why it is not 100% error anytime, because there are a lot of variables which can play a role as to why you cannot always be 100% sure. So you're 95% sure that if you see an association between smoking and cancer in your study, it is because your results are accurate and not because of chance. All right. So in other terms, you're 95%, you are less likely to commit a type 1 error. All right. So basically, if for instance, now in type 1 error, what did we see? Population, there is no association between smoking and cancer. And in your study, you saw there is an association between smoking and cancer. This is a type 1 error. And I explained this well in this diagram. Okay. So we saw type 1 error, where the population says that there is a no association between smoking and cancer. But if you see something, there could be likelihood of type 1 error. Likelihood, not that this is type 1 error. There could be a likelihood, a chance of type 1 error. All right. And that's why it is so important to investigate a lot of other factors. All right. Maybe in your sample, it is not just smoking which is causing cancer. You may find a lot of, say, other variables which are influencing the relationship between smoking and cancer in your sample. You could see that individuals who are smoking, okay, but they have, say, they are also chewing tobacco. It is this set of individuals who are more likely to suffer from cancer. All right. So now this tobacco chewing is acting as a confounding variable. Now I'll talk more about confounding variable in your next lecture, but basically what am I trying to say is that when there is nothing in the population, in the wider population, and you are finding something, there could be a probability of type 1 error, meaning you need further investigation before you are sure. Okay. All right. So yes, so over here, looking at the p-value is very, very important. Why? Because this will give you 95% surety of your results. All right. And the conclusion over here is lower the p-value, less chance of type 1 error. Meaning when you have p less than 0.001, p is equal to 0.008, these are called as, say, lower p-values. Lower p-values are a good likelihood that you have minimum type 1 error. Okay, less chance of type 1 error. Low p-value, good thing. All right. Then when you have, say, moderate p-value like p 0.01 and 0.04, stuff like that, these are called moderate p-values. Not that your chances of type 1 error are always high, but it means you need to consider, is there a missing piece over here? Are there any other biases, or are there any other confounding variables that I need to consider? Or is it because I have low power of my test, meaning I have a very small sample size to actually make big statements and results? So many things you have to consider before just claiming that because I saw there is an association between smoking and cancer, that is why it's happening in the population. No, you may have seen it, but it is not always representative of the population. You need to investigate your sample population much more thoroughly. All right. And then when you have P is say greater than 0.05, which is say your non-significant finding like 0.08 or 0.13, weak P value, meaning there is high chance of type 1 error. All right. And meaning you, if you say, if there is say no association between smoking and cancer, probably yes, it could be because of many other factors. All right. And you cannot generalize your finding to the wider population. As I said, there could be no association between smoking and cancer in your study simply because you have a very, very small sample size to give you sufficient power to your statistics. Or it could be because 80% of your students which are there in your sample, they are health science students and they take good care of themselves holistically, even if they are smoking. So maybe they are exercising well, diet, they are young, many factors playing a role as to why you could not see an association. All right. So basically to minimize type 1 error, guys, yes, you have to practically try to have a good sampling approach, good data collection approach. But at the end, it is very, very important to acknowledge various other factors which may play a role in the association between your main IV and DV. Okay, so what am I trying to say in this lecture, guys? It is very important to understand this concept of minimizing errors, minimizing biases. All right, this concept is very holistic in nature. Okay, so you can't just consider one thing. Okay, you can't compartmentalize things. The whole picture will make much more sense, meaning when you look at the p values, when you look at the effect size, when you look at the power of the test, when you look at various biases which may play a role. Okay, when you look at everything holistically, then you will be able to comprehensively and confidently conclude whether you are at risk of type 1 error, or maybe there are these certain characteristics in your population which you simply have to acknowledge and not generalize your result to the wider population. Okay, so very, very important, try to understand that you need to look at this picture holistically. And this makes little sense in theory if you don't have the opportunity to do it in practice. And how would you have the opportunity to do it in practice? When you actually do hands-on research. So if you are, say, a research student, maybe say a PhD student or a honors student, that is when these concepts, these theoretical concepts that I'm explaining to you as part of this epidemiology unit will make much more sense when you apply it in practice. Okay. So as I said, epidemiology is like the theoretical foundation for you to do real life research. So right now, appreciate this in terms of understanding concepts. This all makes much more sense and logic when you apply it in real life, when you actually do real life research. All right. So now, second concept is effect size. So how do you minimize type 1 error? The second thing is by considering effect size, and effect size plays a very, very big role. Guys, please understand one very, very important thing. P values by itself, they do not make sense. Okay, P values and effect size are like best friends. Okay, you cannot just, because you, for example, you may have P values which are less than 0.001 and you'll become very happy that, oh, less chance of type 1 error because I have very low P values, meaning I have very good results. But if you have P value less than 0.001, but if you have an effect size, so you have a strong P value, okay? But if you have an effect size which is low, which is very, very weak, so strong P value, weak effect size, meaning there is still a risk of type 1 error, which you may have to acknowledge, okay? Then majority of the cases, strong effect size will automatically result in strong P value, okay? In majority of the cases, strong effect size, strong P value, meaning you are much more confident that your results are not just because of chance. You are much more confident that you are less likely to do a random sampling error or a type 1 error, okay? So the best scenario is strong effect size, strong P value, all right? When you have strong P value and a very weak effect size, don't be very confident or happy, meaning you still have to investigate the question further, all right? So as I said, please appreciate this lecture in terms of theoretical concepts. translating this into a research project will make absolute sense. But for you to translate something in practice, you need to understand the theory, the foundation first, okay? And that is what this epi unit is doing for you. Learn the theoretical concepts, and your research project will help you to understand how do you translate this in practice, okay? All right. So, yep. So effect size. So what is effect size? Effect size is a standardized measure. And I also speak about effect size when in your tutorial 4. Okay. So the following tutorial for this week. So effect size, basically, guys, it's a standardized measure. What does a standardized measure mean? It means that you can compare effect size across research papers. Okay. So you have a paper by Smith et al. And you have the other paper by Daniel et al. Okay, you can compare the same effect size across different papers. So that's why it's a standardized measure. Standard meaning the same unit you can compare across things. So it's like kilograms. Okay, so my weight, your weight, everybody's weight. Weight is a standardized, kg is a standardized unit. So it's a common unit for comparison. All right. So similarly, that is what effect size is. It's a standardized measure. All right, so what are the various types of effect size which are most commonly reported in epidemiological studies? You have Pearson's correlation coefficient, okay? And I talk more about how do you actually do Pearson's correlation coefficient in your tutorials, okay? That's why all of your lecture tutorials are so interconnected. Okay, so Pearson's correlation is denoted by a small little r, all right? So like R for Rati, so small little r, all right? So Pearson's correlation coefficient will give you a R value. This R value is a standardized measure. It's an effect size. Then you have odds ratios with confidence interval. So the confidence interval are an indicator of effect size as well. Okay, and I teach you again how to calculate odds ratios in SPSS. Of course, you learned how to calculate odds ratios on paper. But as I said, when you have a big sample size in epidemiological studies, they have very, very big sample size. You don't do hand calculations. You do it on softwares such as SPSS, for example. Okay, so in both cases, be it Pearson's correlation or odds ratios, as I said, greater the effect size, which means your results are more, say, representative of the wider population, which means less chance of type 1 error. Okay, so effect size, strong effect size, your results are very similar to what you see in the real life, the bigger population, therefore low chance of type 1 error. All right, and in terms of, say, confidence interval, remember the concept of dispersion, which was spoken and explained to you in your week 3 tutorial. So basically, with confidence interval, narrower the confidence intervals, less dispersion, meaning stronger effect size. Okay, and we'll be going through these examples in the coming slides. Okay, and strong effect size is, which means less type 1 error. They are inversely related. All right, so Pearson's correlation, as I said, it is denoted by a small little r. And these are just rough classifications, okay? The classifications actually depends upon the literature. So basically, say maybe in physiotherapy, a effect size of say 0.3 is actually considered a moderate effect size, not say a small, but a moderate effect size. But maybe say in say clinical sciences, randomized control trial, effect size of 0.3 is actually considered very weak. Okay, so these are more representative of the literature of the studies which are done in your area of expertise. Okay, so roughly small effect size, less than 0.3, medium and large. All right. So now with in terms of odds ratios, we have learned how to calculate odds ratios on paper. Okay, so basically remember the odds ratios of 1, meaning exposure and disease are unlikely to be associated, meaning there is no association between smoking and cancer, for example. Okay, so when you have less than 1 odds ratios, meaning the exposure may reduce the risk. Okay, so for example, you eat fruit and veggies, this decreases your risk of cancer. So this is a proven thing. Okay, and when you have greater than 1 odds ratios, the exposure may increase the risk of disease, like red meat intake and cancer, smoking and cancer, things like that. All right. Then, for example, the odds ratios, when you have a bigger odds ratio number, okay, and you have a smaller confidence interval, that is called as a strong effect size. Okay, so say the odds ratios of lung cancer was 2 times higher among passive smoker than non-passive smoker. The odds ratios of cancer was 8 times higher among smokers than non-smokers. Okay, so over here I have just said that, yeah, odds ratios of 8 meaning a stronger effect size, but please, what is very, very important, odds ratios and confidence intervals are best friends. Okay, this is just to simplistically explain to you. I wouldn't interpret odds ratios without its confidence intervals. Narrow confidence interval, strong effect size. Okay, so confidence interval are the two true representative of effect size. All right. Okay. Then you have a relative risk. We learned how to calculate relative risk. All right, so the same thing over here. So with relative risk, again, a majority, as I said, it is generally used in clinical trials, all right, with relative risk and prospective cohort studies. So with relative risk, when you have one, meaning the risk of two groups is the same, meaning say there is no difference between the intervention and the control group. Okay, so your intervention, it's not that your intervention is leading to weight loss. There is just no difference in weight. At the end, if there is no difference in weight loss between the intervention and the control group, meaning your intervention is not really working. Okay. Then you have less than 1 risk ratios, which means that people exposed to that factor, yes, they have decreased risk of the outcome, meaning, yeah, the same thing, fruit, vegetable intake and cancer. Or else it could be that people exposed to a factor. So for example, it could be your intervention group is exposed to your intervention, which could be say calcium supplementation, and at the end they have a decreased risk of fracture. All right, and the control group, they just had a placebo and they have an increased risk of fracture. All right, so meaning your intervention is working. All right, then you have greater than when people exposed to the factor have an increased risk of the outcome under investigation. Again, it depends upon what research question you have. Okay, so it could be that, yes, individuals who started smoking, in this case, they were at high risk of cancer. So more number of people got cancer if they were smoking. If they were not smoking, in the other group, you're say, I'm talking about case control studies now in this case. Okay, so now your cases are individuals who are smoking, more number of people got cancer. Individuals who are not smoking, some of the people did get cancer, but these number of people are less than those individuals who are smoking. Okay, so over here it could be, this is how you could interpret the risk ratios. Does that make sense? Okay, so basically the risk ratio explanation is completely same as what you had in your week 3. I believe that is where we did talk about associations. Okay, so there is no difference in that. This is again just the same thing. Okay, so the group consuming red meat 2 times at more risk of cancer, smokers 8 times at more risk of cancer. But remember, relative risk, again, you have to interpret them with the confidence interval. If you don't have the confidence interval, the relative risk by itself doesn't make sense. Okay, so you need the confidence intervals. All right. Okay. So now what is the difference between significance and effect size? All right, so now effect size is definitely different than significance, the concept. Significance, when you say, you are saying you're 95% confident that the results which you have got, they are not by chance. Okay, so you're 95% confidence that your results are accurate. Okay, effect size tells you the strength of your association. What is the strength of your association between smoking and cancer? Okay, so now for example, over here, look at the diagram. You found in your study smoking is associated with cancer. You had an effect size of 0.3 and you had a p-value of 0.02. Now over here, the p-value is also very moderate and the effect size is also pretty low. Okay, and so basically, if I have to say this is 0.3, this should be 30%, not 25%. I'll change this for you guys. So basically 0.3 is 30%. So basically I'll not say this as 25. Okay, I'll just explain this as 30 and I'll change it in your slide. So guys, over here, basically this entire circle is cancer. Okay, so think of this entire circle as cancer. So the variance, smoking is explaining 30% of variance for cancer. What does it mean? It means that 30% of cancer is attributed because of smoking. All right. So that's not a very, very big percentage. It's just 30%. So what's happening to the other 70%? The other 70% of the cancer is, it could be because of various other reasons. It could be because of red meat consumption, tobacco chewing, stress, UV radiation, so on and so forth. Many, many other reasons as to why your sampled population may be suffering from cancer. Okay, so this is what is effect size. It means that yes, you found a significant association between smoking and cancer, but don't get very happy, because it is only explaining 30% of the variance. 70% of the variance is because of many, many other reasons as to why your sampled population may have cancer. Does that make sense, guys? This is the difference between significance and effect size. That's why effect size is so very much important. Now, if the tables were turned and if you had, say, 70% of the variance in your study sample is because of smoking, meaning if your R value was 0.7, and your P value will automatically go lower in this case, okay? Because majority of the time, that is how the relationship works, okay? I'm just going simple right now. If I was explaining quantitative statistics, I would have told you various other permutation combination, not required at this stage. So if your R value is 0.7, which is 70% of the variance explained by smoking, your P value would be, say, is equal to 0.001 or 0.008 or something, okay? In this case, you have much less chances of committing a type 1 error, because your effect size is very strong and it is highly representative of the wider population. Now, guys, when I talk about wider population, I'm not talking about the entire Australian population. Remember, your sampled population is university students, adult university students who are attending University of Canberra. So the population you can maximize this to is the university students in the Canberra region or the ACT region, okay, the maximization, all right? Or if you are just studying, say, health science student among University of Canberra, it could be, say, the wider student cohort population who are attending University of Canberra, okay? So now when we talk about population, you will have to appreciate that it is not always the big national level population, all right? You can't even reach that stage if you do not have a strong sampling technique, okay? So your sampling technique is only representative of University of Canberra, all right? So your wider results could be only applicable, to university students attending University of Canberra. Okay, and if you had, say, a bit more good sampling technique, okay, so maybe you considered, say, university student going to ANU and UC and the other smaller campuses which we have, which is, say, QUT and all of those, okay, so your smaller other campuses, then yes, in this case, your findings could be representative of university students within the Canberra region. Does that make sense? So when I talk about population in this case, it is not always the Australian population. It could be only your Canberra region population, or it could be even smaller. It could be just University of Canberra population, and you have a tiny sample size of 50 students from the health science batch. Does that make sense, guys? Okay, so this is what it means by effect size, and why effect size is a very, very important indicator for you to gauge your probability of type 1 error. Okay, so that's why it's important to consider effect size and p-value together. So always remember, effect size and p-value are best friend. You need to report them together, all right? Some students, not some, actually many students, they have this habit of just writing p-values in their research paper without the effect size. That makes no sense, guys. These are best friend, okay? These are like, okay, not even best friend, maybe they are more than best friends, okay? They are like Romeo and Juliet, okay? Don't separate Romeo and Juliet, okay? There's a sad ending if you separate Romeo and Juliet, okay? We don't like sad endings. At least I don't like sad endings, okay? So you need to have both of these together. Effect size and p-value, they go hand in hand, all right? So I hope this concept is very clear, guys, okay? So yes, how do you minimize effect size? Now we spoke about relative risk and things. We spoke more in terms of, say, R, Pearson's correlation, R value. Now we'll talk about effect size in terms of confidence intervals. All right, and the concept lies in dispersion. The concept of dispersion I had briefly explained in your tutorial, week 3 tutorial. Okay, so basically these are the various, in your tutorial I had explained in week 3, these are the various indicators of dispersion. Okay, we will be talking about 95% confidence intervals. Okay, because as I said, all of this is more spoken in terms of quantitative statistics. For you to understand the concept of dispersion, we just need to select one of these 6 and go ahead with the concept. All right. So yes, I've explained to you the concept of mean or the central line, all right, the central tendency. You know the dispersion, narrower the dispersion, stronger the effect size, which is what I had explained to you, okay. Error of deviance is basically the distance between your sampled population cases and the central mean tendency, okay. More distance, greater error, greater chance of type 1 error, okay, and poor effect size. Okay, so we don't want that distance, we want it narrow. Narrow is good, okay. Narrow dispersion is good. Less error meaning there is less distance, so less distance is good, and narrower dispersion is good. And what does this mean graphically? I'll show that to you in your coming slides. Okay, so basically remember, less dispersion, better are the results because they indicate stronger effect size, meaning less chance of type 1 error. All right. Okay, guys. So this, you see this line over here, this linear line. This line is called as your central tendency. Okay. So this is, say, the on an average how your population is, okay, or should be. And these tiny circles, these are your individual cases. Okay. So like I am participant number 1, which could be this. Then you have Sarah, participant number 2. This is Stephanie, participant number 3. So these are actually individual cases within your sampled population. Okay. So yes, on an average, your central tendency is this. This is the, okay, this is the main line of regression is what we call, but I won't go into all of those details. Basically, this is the center line. And the main thing over here is when the points are closer to the center line, meaning less distance between individual points, and your center line, closer points to the center line, meaning less is the dispersion, stronger effect size, better are your results, less chance of type 1 error. Okay, so that is the thumb rule. Okay, when you learn about, say, regression as a multivariate analysis, this makes much more sense to you. Okay, so yes, this distance between the single point and line, that is called as the error. So you know this error or deviance. So this is called as the error or deviance, which is the distance between the single point and the line. So you have less error when you have less distance between the single point and line. So you see these things which are on the line, very, very good. Okay. These which are far away, this will make your data weaker, effect size weaker. Okay. So overall, holistically, when you look at the blue one and the yellow one, you see blue one is much better because the points are much more closer to the line. Okay. But the yellow one, they are scattered like everywhere. Okay. So you hardly have anything which is closer to the line. A lot of points are scattered everywhere. Okay. These scattered points, guys, the more further the individual points are away from the main line of regression. Okay. So this strong solid line, the more away these points are, these points could be your outliers. Outliers meaning those data points or those sampled cases or those individual participants who may not be following the normal trajectory of your overall population. Okay, so it could be that on an average, okay, majority of them are scoring credit. Okay, outliers are not always bad. Okay, and that's why I'm using this unique example. So on an average, the class is scoring credit, but you have these 1, 2 very unique cases which are, say, HDs. Okay, so one is like, say, fail, and the other is like, say, HD. Okay, so that's why these are outliers. Okay, so they are making the confidence interval much more wider. But if these points were removed, then your confidence intervals will become much more narrower. But now the question comes, is this representative of my sample population? That is something which you need to answer going back to your research question. Therefore, guys, when you have a data set and when you are finding results, outliers or wider dispersion is not always in terms of good or bad. I'm explaining to you in good or bad only because you're learning this. Majority of you may be learning this for the very first time. So you need to understand the theoretical concept. But you always need to go back to your research question to see whether these outliers are important for your study research question, or whether these are, say, just contaminating your data and it is okay for you to take them out for you to get, say, much more structured results telling the same story. Okay, so which one is your case is very difficult for me to just give you a simple answer, because there is no simple answer. It depends upon your research question. All right, so I hope it makes sense, guys. But overall, for you to just understand the concept of dispersion, this is what it means, which is wider the points are, more distance between the line of regression and your data points, more dispersion, lower the effect size, and greater the error or greater the deviance. Okay, so this is what it means. Similarly, this is just an other example. These are called QQ plots. Okay, so again, this is your line of regression. Okay, this is your central tendency basically, and you see how the points are so beautifully close to the line of regression, meaning this has less dispersion and therefore it has a stronger effect size. Over here, you see how the distance is much more, meaning this will be having a lower effect size. All right, and this will be having greater chance of type 1 error. Okay, now you have your bar charts. So over here, the main fundamental is longer the error bars, larger is the deviation from the mean. Okay, so mean the average. Okay, so over here, if you see in males, in case of boys, okay, this is the error bar. Okay, this long line over here, this is the error bar. You see the line over here is so much more longer, but in girls, the line over here is so much more tighter. Okay, tighter the line, meaning less dispersion, stronger the effect size. Longer the line, meaning greater dispersion, meaning poor the effect size. Okay, so over here in male, you have, what is this mean age of participants? Okay, so you have male on an average. So the average age of the sample is 15 years, but the standard deviation is greater. Okay, this number being bigger, meaning you have greater deviation from the mean. Okay, so think of it as the this line of regression. Greater deviation from the mean, meaning the distance between individual points and the line of regression is much more greater. That greater is not good. Okay, not good in terms of your sample. As I said, good or bad depends upon your research question. Okay, this is just for you to understand the theoretical concept. Okay, so over here you have a bigger standard deviation, but you see the girl has, for girls, the standard deviation is much more smaller. Meaning, yes, almost all of the girls in your sample, they are lying around this 13 years of age mark. Okay, so the standard deviation is much more smaller, so the error bars are also much more smaller. Okay, so meaning less error. This is larger error. All right. So now moving further, this would make a lot of sense if we had, say, face-to-face class. Okay, but I'll just answer this for you. So for example, you have BMI, which is associated with depression over here. All right, and you had two samples in which BMI is associated with depression. Okay, both the sample, you have the same BMI of 28, BMI of 28 and sample 1 and 2. 28 BMI meaning they are overweight. Okay, so but in sample 1, you have a confidence interval of 23 BMI and 32 BMI. So you see 28 lies in between. Okay, sample 2 has 27 BMI and 29 BMI. Now remember, you narrower the dispersion, it is stronger the effect size, better the confidence interval. So over here, the yellow one is a better result. It is a stronger effect size because the confidence interval is narrower, meaning majority of your participants are telling the same story. All right. So yes, why is less dispersion better? Because your findings are then more generalizable to the larger population. Now, as I said, when I talk about population, remember it is not always the Australian population, national population. Okay. So I explained you this concept very well. So please keep that in mind. So yes, but your findings are definitely generalizable wider to your sampled population. All right. So that's why less dispersion is better, because you have more credibility, more confidence in your finding that your findings are applicable beyond your sampled population. How much more beyond? That depends upon your sampling technique, okay, and other factors such as your research question as well. All right, then you have, of course, with less dispersion, you have less chance of type 1 error. And this means that fewer confounding factors which are influencing the IV and the DV. Okay, so yes, a lot of things go on, or a lot of things are credible when you have a tighter dispersion, meaning a narrower dispersion. Okay, narrow dispersion, stronger the effect size. Okay, so I hope guys the theoretical concepts of effect size and significance are clear to you, because these are very important fundamental concepts for you to understand and interpret research papers correctly. Okay, because now you will have the capacity, the scholarship to critique research papers. Okay, because now you won't just simply become happy because somebody has a p-value less than 0.001. You will look at the effect size, you will look at the dispersion, which will help you to scholarly critique that, hang on, are these results really applicable to the wider population, or is this just applicable to the small little population of nurses that they surveyed in the Royal Brisbane Hospital, and that's about it. They can't go beyond that. Make sense? Okay. All right. So you have one more concept, which is which you need to understand. What is the difference between statistical significance and clinical significance? This is very important, guys. And if you do not have the scholarship for the same, a lot of say writers can very smartly say that because the results are statistically significant, they have done a great job. No, your scholarship over here lies, are these results clinically significant as well? Okay, so you may have a great effect size, you may have a good p-value, but is this clinically significant? Okay, so that is very important. So now over here, for example, statistical significance does not always mean clinical significance. And I'll give you an example. So clinical significance means the significance which you need to achieve for you to see real life outcomes. Okay, real life outcomes are very, very important to see a clinical impact. So what has been seen in the literature is if you reduce your BMI by 5 kgs, okay, BMI reduction by 5 kgs. So if you lose weight by 5 kgs, this result in lowering of your high blood pressure by 3 mmHg. Okay, so if you are a high blood pressure patient and if you reduce your weight by 5 kg, but of course there are a lot of other clinical conditions like you are overweight and obese in the first place. Now when I say you, please don't feel offended, as I have told you in the first lecture. Okay, so yes, this is clinical significance. 5 kg of weight reduction actually results in your decrease in high blood pressure for high blood pressure patients. Okay, now if you have research papers which says that, oh, in the intervention group, we saw that there was a reduction of say 2 kg weight. All right, and they said that this is therefore applicable in the future for say health conditions such as heart disease and dyslipidemia and blood pressure and all of that. Now you need to question, is 2 kg weight reduction really going to help individuals on an overall population level to reduce their blood pressure? This is a very big claim, overgeneralization, which is made by the author when we know that a 5 kg of weight reduction minimum is needed to decrease your blood pressure by 3 mmHg. Okay, so this is what is important. Statistical significance does not always signify clinical significance. For clinical significance, you need to look at the clinical guidelines. How are clinical guidelines made? When a lot of randomized controlled trials or studies which have good quasi-experimental design, prospective cohort design, they are all compiled together, and then you have level 1, level 2, level 3 degree of evidence. Okay, so over here, if your clinical guidelines say this is the level 1 evidence For example, 5 kg weight reduction, you have 3 mmHg decrease in your high blood pressure. Well, if this is a level 1 evidence, and if one study which is done in say India, China or Australia by a tiny little research group has shown 2 kg weight reduction and they are making big claims, then they should be mindful about it. Even if you have a big say study, a big fancy research group in the United States who have surveyed say 1,000 participants and they have seen a 2 kg weight reduction, but they haven't shown clinical significant results, then that is questionable. Okay, sometimes they may do just 2 kg weight reduction and they may say that the weight blood pressure reduced by 0.01 mmHg. Is this really going to make a impact on health and quality of life? 0.01 mmHg of blood pressure reduction. Okay, so that is again a question which you need to ask as a clinician. So as a clinician, you should never forget your clinical hat. Okay, you always need to have it on to see that, yes, you reduced weight by 2 kg. Some of the researchers would be in our intervention group, the weight reduced by 1.37 kgs. And we saw a blood pressure reduction by 0.032 mmHg. Is this clinically significant result? Yes, you found statistical significance. Yes, you had a very strong effect size. But what does this mean in real life? If I have, like, say, a patient population sitting in front of me, okay, can I translate this into a clinical setting? Of course, in clinical setting, you're not talking in terms of population level, you're talking in terms of individual level, but you always have to think that, would this make sense clinically? All right. And now, again, as I said, it is very difficult for me to just have a generalized statement. It depends upon individual field. Okay, so for example, in the field of dietetics, if I have a blood pressure patient, I would be looking at these clinical guidelines. Okay, I would be recommending them if they are overweight and obese, and if I feel that yes, their history would help them in reduction in say weight. Yes, if their clinical history says that, I would be looking at individual papers and saying that, okay, let's try to reduce your weight by 1.37 kgs. This will result in say 0.07 mm is whatever Hg of blood pressure reduction. Your patient will be like, will this really create an impact? No, I will look at this clinical guidelines and then I'll take slow and steady steps for them to achieve this 5 kg weight reduction. Does that make sense? That's why clinical significance is so important. There is no one set golden rule for clinical significance, guys. One of the best place to refer for clinical significance, as I have hinted many times, is look at your clinical guidelines. Okay, if you don't have strong clinical guidelines or evidence available, then go as per the NHMRC level of evidence, which is, you may go as per your experience, as per your clinical consensus, which could be your 30 years of experience showing that. Okay, so yes, you have seen research, but then look at your clinical hat, look at the evidence. If there is no evidence, which could be very well in some cases, then you look at some smaller things, which may not have say NHMRC level of evidence, but then comes in your experience of this 30 years, okay, which is called as clinical consensus. All right. So I hope this makes sense, guys. Okay. So again, entire intention is to turn these theoretical concepts and help you to understand how and where are they applicable in real life. Okay. All right, guys. So now the last thing which I want to show you. So guys, this is how tables in meta-analysis are published. Now, meta-analysis are very good level of evidence. Okay, they are level 1 evidence, especially if you have meta-analysis of randomized control trials. Okay, but meta-analysis are good, definitely. They are strong evidence. Even if not all meta-analysis are level 1, they are still strong evidence because they compile a lot of study and they do their own statistics, right? So in simple terms, now over here, if you see, for instance, what I want to show you, you look at this dotted line over here, this vertical line, look where my mouse is hovering. Okay, this is the minimum amount of say result you need for clinical significance. Okay, so this is the minimum odds ratios you need for clinical significance. Okay, so this data is from say a work which we are doing. So over here you have say increase in HbA1c level in type 1 diabetic patient, and you have decrease in HbA1c level in type 1 diabetic patients. Okay, so now when you look at decrease of HbA1c level, that is what you want for a type 1 diabetic patients, right? You don't want increase in HbA1c level. Those who are not familiar with that, HbA1c level C is an indicator of, in very layman terms, your blood sugar levels. Okay, so higher blood sugar levels, we don't want that in type 1 diabetes. You want to decrease the blood sugar levels. But when I say decrease, it is not hypoglycemia, meaning you want to moderate, you want to regulate it. Okay, so this dotted line reflects the minimum odds ratios needed for clinical significance. Okay, so now if you look over here, guys, if you look, the minimum odds ratios which is needed is minus 1.529. Okay, so this line over here, it represents this. Okay, so this is the minimum odds ratios which you need for clinical significance. And if you see, all of these are meeting that criteria. Okay, so yes, and then you have, these are your 95% confidence interval around the odds ratios. Okay, now if you look over here, you will say the effect size, this ES is effect size. Okay, so this effect size, which is odds ratios in this case, is minus 2.149. All right, so if you see 2.149, so it is sitting somewhere over here. This is by Vernon. So Vernon is over here. Okay, so you will say, oh wow, they have really reduced HbA1c level considerably. So they have reduced HbA1c level, say, by 2.146, okay, percentage points. All right, so you'll be like, wow, this really has high reduction. Okay, so this must be the strongest study of the group. But hang on, it is still not the strongest study. Okay, so this effect size is strong, but what is the weighted contribution of this study? The weighted contribution of this study is only 12%. Now, this weighted contribution is on several factors. So basically, what is the total sample size? Then the weighted contribution also depends upon, say, the odds ratio. So how many outliers were there, those individual data points, how many outliers were there? Okay, so, and all of this considered, you see over here, this is the error bar. We spoke about error bar. I had shown you vertical error bars. These are horizontal error bars. Okay, so where is my mouse? Yeah. So horizontal error bar. So these longer the error bar, greater is the dispersion, poorer is the effect size. So that's why the contribution of this study, when you do a meta-analysis, the contribution, the strength of this study in explaining the variance, which is reduction in HbA1c level, is only 12%. Okay, so which study is explaining the maximum variance is this one by Nelson. Okay, so it's 41.38%. So this study is explaining the maximum variance in reducing HbA1c level, meaning majority of the people in this study are saying the same story, and therefore they have a more reliable effect size. Over here, we are not talking about just higher effect size, it is more reliable results, more robust results. Okay, so if you see over here the confidence interval, so Nelson 2012, this has really tiny dispersion. Okay, the error bars are really tiny, and the bigger the box, this center box, the bigger the box, meaning greater is the contribution of this study in showing you clinical significance. Does that make sense? So you see how this box over here is so close to the clinical significant line. So this is a much better study. Does that make sense? Even though you may have a bigger effect size over here, okay, but this is a much better study. All right, so you may have reduced HbA1c over here by 2.149, so reduction is in minus. Okay, so minus 2.149. You may have reduced over here not that much, minus 1.4, but overall everyone is telling consistent results. The consistency over here is not as much. Okay, so these findings are much more reliable, therefore it has the greatest contribution. Is this absolutely clear, guys? Okay, this why did I particularly take the example of meta-analysis? Because this will really help you next time to interpret meta-analysis forest plot. This is called as forest plot when you see this in real life papers. Okay, so therefore this concept of dispersion, the concept of effect size explained in a meta-analysis, so it makes absolute sense when you look at research papers, because a lot of meta-analysis are epidemiological studies, okay, done within the epidemiological forte, and therefore it will make a lot of sense if you know how to correctly interpret this. All right, so again, sorry, I went back into my quantitative research, but I couldn't help myself. I just had to share this example with you, which brings all of the points together. Okay, so yes, I hope this has been helpful for you guys. So yes, moving further, what are the sources of random error? This is just an say quick summary, which is say biological variation. So what does this mean? For example, I'll just go by the examples. The explanation you can read. So for instance, you have blood pressure or body temperature. These are likely to vary between measurements. Okay, even like blood sugar levels are likely to vary between measurements. So these can be sources of random error. All right. Sampling error is again a source of random error. Okay, so error caused by random influences of who is selected for the study. As I said, sampling techniques are therefore very important. Sometimes you cannot help yourself and your sampling error could lead to random error, all right, potentially. For example, if you do a convenience-based sampling, like, I have done. So I have to acknowledge, say, sampling related errors as part of my overall study. Okay, that my study could be susceptible to sampling error because I have done convenience sampling, but that is the only practical tool which I could use for the pilot project. Make sense, guys? Okay, so then you have measurement error. So what is measurement error? Meaning, say, weight of an individual can vary between measurements. Okay, and this could be because of the tools which you used. Okay, so for example, validity and reliability I had explained to you very well in your last lecture, I think. Okay, so for example, if you're using a scale but which is not calibrated, that's why calibrated tools are so important. Now, again, how do you calibrate? That is a research method subject. Okay, so, and it depends upon the tool. So for example, as a dietitian, one of the main tools which I need for calibration in a study which is looking at weight status would be, say, the weighing scale. Okay, so I need to calibrate my weighing scale. All right, so if my weighing scale is not calibrated, this can lead to measurement error. Okay, so the tool which you're using to measure something, that needs to be valid, reliable. Okay, if not, this can lead to measurement error, which can increase your chances of type 1 error. Okay, so all of these can increase your chances of type 1 error. Make sense, guys? Okay. So now, how to minimize type 2 error? All right, so type 2 error can be minimized predominantly when you're looking at the power of your study. Okay, so your study should be sufficiently powered. So what does sufficiently powered mean? Meaning you need to have sufficient sample size. If you don't have a sufficient sample size, you're very, very likely to make type 2 error. Okay, so what was type 2 error? For instance, population says there is an association between smoking and cancer, but you say there is no association between smoking and cancer. This could be very likely if you don't have sufficient power to your sample. Okay, meaning you don't have a sufficient sample size. All right. So again, how do you calculate sample size? This is more quantitative research. All right, not applicable in this unit where I teach you sample size calculation. This is quantitative statistics. So calculation of sample size is something which you will learn elsewhere, but just a few key indicators that you have to remember is that your study is generally powered to 80%. Generally, I'm saying, okay, statistician may decide else, which is more, say, applicable to your population. But yes, your study needs to be sufficiently powered. So it is 80%, meaning 80% of the time, we can correctly identify that the IV and DV are related. Okay, that is what it means. It means your study is sufficiently powered to 80%, meaning 80% of the time, you are correct in identification of IV and DV being related. All right. Then generally studies have a precision of 5%. Meaning how much sampling error, type 1 error is acceptable for the study. Okay, so meaning 95% your confidence and 5% is error. Okay, and then you have oh yeah, that point I have said over here. So generally studies have a 95% confidence interval, meaning 95% you are confident that the findings are not due to chance. All right, so when you do sample size calculation, they ask you for the power, which is generally 80%, precision of 5%, meaning how much sampling error is acceptable. So 5% is acceptable, 95% you need to be confident. Together this becomes 100%. Okay, so 5% error is what you're allowing, 95% you need to be confident, And sample size calculation also takes into consideration majority of the time dropout rates, okay, meaning people who will leave your study, therefore your sample will become smaller and smaller, which could then impact the power of your statistics, meaning your power becomes weaker because your sample size is reducing, therefore you are more likely to commit type 2 error. All right. So type 2 error is also very sad, guys, because there is an association, but your study just cannot show it. Okay, so a lot of studies, pilot projects, which are underpowered, meaning not having sufficient sample size, they are at risk of type 2 error. Okay, so for example, I'll give you a real life example over here. So now, guys, as I said, I'm doing this picky eating study, right? So in this picky eating study, my biostatistician mentor, my supervisor, we calculated a sample size of 360 people, I think, okay, to do this study. Okay, so I need 360 people. That will give me sufficient power to undertake statistical analysis, okay, meaning which is 80% powered, 5% precision, and 95% confidence interval on a two-tailed test. Okay, so, but he said to actually try collecting data on at least 400 people. Okay, so I have, say I have a allowance of, say, around, I think 20% extra or so people. 400 plus is what he advised. So I have accounted for 20% dropout rate, because just in case I have people who are not completing the questionnaire, they take my questionnaire but they don't complete it. If I target 400, I may finally reach, say, 375. Does that make sense? Okay, so it's very important to account for dropout rate. All right, so then you are not underpowering your study. All right, so I hope all of these concepts are clear, all of these terminologies are clear, because these are very popularly used, commonly used within the epidemiological space and overall general research space as well. All right. Now, guys, we'll quickly go to biases, which is a systemic error. Okay, so you have a systematic error, which is called as biases. So biases, again, it exists all types of research, study design. You cannot eliminate it. You cannot eliminate anything. Okay, you can only minimize it. So our aim is minimization of biases. Okay, so if you don't try to minimize biases, this will impact the reliability and validity of your finding, meaning you cannot generalize your finding to the wider population. You're more likely to commit type 1 and type 2 errors. All right. So now biases, they are there at all stages, meaning you have at your planning stage, at implementation stage, at data analysis and publication stage as well. Okay, and we'll be going through all of these biases. So I'll be giving you examples of each. All right, so first you have your planning stage biases, which are very likely to be at planning stage. So guys, I have selected the most common type of biases. Okay, there are many other types of biases, and a lot of these biases, guys, I have summarized them for you, where I have, I had given you pre-readings for your reliability and validity, threats to reliability and validity. They talk about a lot more biases, because as I have said over here, biases impact reliability and validity, meaning biases are a threat to reliability and validity. Therefore, a lot of these other biases are also covered in those post readings for reliability and validity. And as I said, rest assured, that is just for your FYI reading, okay? Threats to reliability and validity, but they are nothing more than biases. All right. Okay, so design biases, meaning where your study is poorly designed, where you don't have your aims and objectives clearly defined, you don't have a strong method. Okay, so this is an entire design bias. So you have a very poor design. Okay, so basically, how do you address this bias, which is important, which is you need to have clearly defined your aims and objectives. You need to use validated tools for your data collection, for your methodology. All right, and where possible, if you're doing, say, intervention trials, then yes, you need to have, say, blinded data collection procedures, okay, such as the participants not knowing if they are in intervention or control group, researchers not knowing which participant is in intervention or control group, stuff like that. All right, so now, guys, with objectives, again, this is part of research methods, and I can't teach you over here. But please remember, your objectives need to be SMART, S-M-A-R-T, okay? Specific, measurable, attainable, reliable, time, appropriate, something like that. Okay, so they need to be SMART. And other thing very important is that in simplistic term, what I keep in mind when I design my objectives, can I measure my objective and can I analyze my objective? If I can answer these two questions, meaning I'm on the right track of designing correct objectives. Okay. So yes, your objective needs to be measurable and it needs to be analyzable. Okay. If you cannot do that, there is no use of having that objective, because whichever objective you have, you need to be able to do analysis on those objectives. It could be, say, qualitative analysis, quantitative analysis, mixed methods analysis, but you need to find the result of your objectives. Objective in simple terms is like asking a question, which is, this is what I want to find. Is there an association between smoking and cancer? Okay. But what if, I mean, nobody is that dumb when I'm using such a simple example, but what if the researcher didn't measure smoking and they measured tobacco chewing? Then how is it asking, how is it measuring the objective, which is there an association between smoking and cancer? Okay, let's make it more realistic. So maybe the researcher has two objectives. Is there an association between direct smoking and cancer? Is there an association between passive smoking and cancer? Now, these are research questions. Okay, now these can be, say, framed as objectives as well. Objectives are basically research questions, but they are not in a question format. Okay, so you will have to identify the association between direct smoking and cancer. So now this is in a statement form. So this is an objective. Okay, but what if the researcher only measured direct smoking, meaning, do you smoke? Okay, yes or no? How many times you smoke and all of that stuff? Okay. What if he didn't measure passive smoking, meaning, what if he's smoking in the household and his wife is there, his children are there, and all of them are exposed to this smoke on a regular basis, daily basis? Then this has its own impact, right? This is passive smoking, right? When you are constantly exposed to that smoke, this is passive smoking. But what if the researcher didn't collect sufficient data on passive smoking? Then he won't be able to analyze that. Therefore, you need to measure, your objectives need to be measurable and they need to be analyzable. So these are the two key things which I keep in mind when I design my objectives. Okay, that they, at the end, I should have an answer for it. And how will I have an answer for it? When I can do some type of analysis on it. It could be qualitative, quantitative, or mixed methods. All right. So I hope this makes sense, guys. Okay. So design bias. Then you have selection or participant bias. So what is selection or participant bias? Where, for example, biases which are happening when you are recruiting participants in your study. Okay, so for instance, as I said, majority of the participants which I'm recruiting in my study, okay, it's good to use my study example because, as I said, there are certain biases which you need to, say, acknowledge. Okay, you sometimes can't even minimize them. So majority of the participants, guys, which I have in my study for the picky eating with genetic and environmental determinants, basically, guys, majority of these participants are Indian participants. Okay, because I have, it started as a snowball technique. One mother telling the other mother telling the so and so forth mother. And then it so happened that majority of them were Indians. Okay, so the network was Indians. Then you had these temples and Indian churches and things like that. They started getting involved. So it just so happened that my snowball technique invited Indian participants. And then what could happen is that mothers who are genuinely concerned that their child is a picky eater, those mothers are more interested and likely to participate in my research, right? Which makes sense. So this is what I'm saying. This can lead to selection bias or participant bias. So it could be participants who are more interested in your study will participate, or this could be, say, this is not in my control. Okay, but what is in my control? What if I just recruited not patients, my participants via online media? Okay, just Facebook, okay, Twitter, Instagram, that's it. But what if I'm missing out on other sources, meaning mothers who are attending community centers, mothers who are attending, say, hospitals, and mothers who are attending outpatients clinic, then mothers whose children, because my study is mom and kids, so mothers who are there in the parent-teacher association in the schools. Okay, so there are so many other sources of recruitment. So that I have tried making sure of, because I I have gone to practically all sources possible. Media sources, radio sources, newspaper sources, community centers and organizations, medical centers. I have tapped all of these doors to make sure that it is not that I'm only recruiting mothers through Facebook. Okay. So basically, guys, this is how you try to minimize this bias by ensuring as much as possible, which is in your control, that you widen your sources of recruitment so you do not have a bias of only a particular type of people participating in your study. All right. And then you have confounding bias, which is say particular type of say age, not rate. This should be race is what I want to say, ethnicity. Okay. Oh, withdrawal rate. Okay, that makes sense. All right. So confounding bias, I have given examples such as withdrawal rate, age, sex, etc. So you control for confounders. Again, there are certain confounders which you can control for. Okay. And in statistics, you can definitely control for confounders. Okay, so when you do regression, for example, multivariate analysis, you have the capacity of controlling for a lot of confounders. Okay, and when you're doing data collection stage, you still have the capacity for managing your confounders. Okay, so for example, I'm making sure that mothers of say variety of say age range are participating, meaning say young mothers to say mothers with teenage kids, or say mothers with older children. Okay, so my age range is 7 to 12, but the mother could be say 21 years of age, or the mother could be say 42 years of age. Okay, with kids 7 to 12. So it is not just restricted to young mothers. All right. So that is how I can try and manage this. You control for the withdrawal rate. One way of controlling for withdrawal rate, there are many ways of controlling for withdrawal rate. First, you account for withdrawal rate. Okay, so in your, as I said, when you're doing your sample size calculation, you account for the dropout rate. So people who will withdraw from your study. All right. The other ways of controlling for withdrawal rate is constantly engaging your participants' attention. Okay, so if you have to follow up with them after say 3 months or after 6 months, you still have some point of contact, so your participants are not bored and they just decide that they don't want to do the study anymore because it's too boring. Okay, so there are various ways of how you can control for the withdrawal rate. All right, now moving forward. Why is it not moving forward? Okay. All right, so then you have again, this is at a planning stage, so you have channeling biases. So channeling biases is, for example, where you are allocating participants favorably, okay, which is going to favor your intervention. For example, this is not in my case because I just have one group. All right, so a good example over here is, for instance, you have a high energy, high protein drink, and you want to see whether the high energy, high protein drink, it improves the lean body mass, body composition in your participants. So you very smartly are recruiting young participants in the intervention group, and then and who are more athletic in nature, and they work out say 4 times a week and things like that. And you're recruiting the not so physically active older participants in your control group. Obviously, you're going to see a change in the intervention group because firstly, they are drinking the high energy, high protein, but because they are say organically more apt to increase their lean body mass because of their age, because of their genetics, because of say their workout regime and all of that. Okay, so this is called channeling bias. Okay, so with channeling bias, one of the way to minimize is, yes, you have blinded data collection, so you don't know who is in intervention control group, researcher does not know, participant does not know. Okay, again, you have clear aims and objectives and outcomes and standardized tools for collection. Okay, so channeling bias, again, different types of examples, different type of study design, different channeling biases. I have just given you one example for you to understand the concept. All right. Then, for instance, you have biases at a data collection stage, the common types. All right. So you have measurement bias. So if a tool or instrument has not been assessed for its reliability or validity, yes, then you have measurement bias. As I said, for instance, if you have a weighing scale and this weighing scale is not calibrated, okay, and what if it just naturally keeps showing that, oh, your participants are weighing 5 kgs less. Okay, so then you'll be like, oh, all of my participants are healthy weight because of my high energy, high protein drink. No, it is because your scale is faulty. Okay, but you did not check that. All right, so I'm sorry it sounds so funny, but obviously you would be very careful of such things. But basically, my main intention for you to understand this concept as simple as possible. Okay, because in books, the way it is written, it can be quite confusing. All right, so yes, what is the main way of, say, minimizing these biases? Using reliable and validated tools, techniques, and methodology. All right. Okay, so then you have interviewer bias. So it is like, for example, if I'll give you a new example over here. I'm tired of giving my picky eating example. You'll be like, she always keeps talking about picky eating. It's only because that's my current area of research and I'm like so passionate about it. And it's like I'm doing that research. But let's use a new example. Okay, so you know how I said I had done, say, a study, I had done a study in India, okay, which looked at the private hospital, moms who were going in the private hospital. Oh, this actually, I'm talking about this in the tutorial. It's like I record one thing before and the other thing late. Well, in the week 4 tutorial, you will hear about this example, which is on me doing my postdoc in India for 2 years, where I looked at mums who were attending private hospital versus mums who were attending government hospital. And what if I go with this bias that mums who are going to the government hospital because they are not economically well off, of course they are going to be deficient in their vitamin D status or iron status and stuff like that. Okay, so that's really bad. Okay, because I'm going with that bias in mind. So that's why if I take their interviews, I'll be like, yeah, she's not having so many iron sources, and yeah, that's why her she has an iron deficiency. No, there could be many other reasons, but I have this bias that no, because they are attending this hospital, they are not economically well off, and that's why they would be having so and so things. Okay, so how can you minimize this? How you minimize this is by data triangulation. Again, this is a research method procedure, but I'll explain it to you. Okay, so what is data triangulation? So for example, you first look at the existing evidence which is out there, meaning the wider literature. What is the pattern? What is the story which is being said in the literature? I've explained you this concept well earlier in earlier slides, right? So first you look at the literature. Second could be your own data collection, which is your own interview records from your participants. Third could be an observer. Okay, it could be an external observer who's looking at, say, your say data collection technique, and then who is recording whether there is actually a bias going on or not. Okay, so yes, this works in some conditions, this does not work in other condition. In data triangulation, you sometimes can have two observers. Okay, so just to see if you don't have an observer bias. Okay, so you can have two observers, and if both of the observers are saying the same thing, that no, Rati is really biased, because when she's questioning them by giving them indirect hints. So it's big. Oh, okay, so you stay in slum areas, so you were not really having a lot of nutritious food to eat, right? So isn't that really a biased question if I'll be framing a question in this way? Like this would like take the participant back, and maybe they will then try to give a favorable answer that, oh yes, yeah, it's because of that reason. Yeah, no, this is like, this is not the right way of framing question. You are a very biased interviewer. All right, don't worry, I'm not like that. I'm just giving an example. Okay, so then you have the Hawthorne effect or social desirability bias. This is what I'm saying, guys. Social desirability bias, when the participants responds in certain manner because they feel that they are under observation, like, doctor is recording their interview or a researcher is recording their interview, stuff like that. So one way of doing this is, yes, being non-judgmental, letting them know that there are no answers which are right or wrong. You just want to know their honest opinion. Everything is going to be confidential, de-identified, all of that stuff. That's why you have consent form and participant interview sheets and stuff like that. Again, all of that is a very research method thing. But basically, you ensure with all of these steps and procedure. What has also seemed to work, guys, in certain cases which I have seen, is having a middleman to record your data. Okay, so what does this mean? So as I said, when I was in India doing the postdoc, I had these mums, right, who we had to collect data from. So what we did was, we had a local person. So this was in tribal mothers. Yeah, so this was in tribal mothers. So this was another study in India in tribal mothers. So now these tribal mothers, we had a localite we trained the localite to collect the data because they found it less overwhelming, less condescending to have say a localite chat with them and collect data. Okay, otherwise we had no intention of being condescending or patronizing in nature, but just they having this say opinion of, oh, a doctor, a researcher is coming to collect my data, they would be giving inaccurate responses. Okay, they would try to give favorable responses. So you don't want that. So we trained localites, we trained local social workers to collect the data, community workers, and this was much more accurate and much more culturally appropriate as well. They found it easier to open up to them. Makes sense? Okay, so the best way of understanding biases, guys, is with lots of examples. The best way of understanding anything is with lots of example. But trust me, if I just give you the textbook definition of social desirability bias or Hawthorne effect, you'll be like, what is she talking about? Okay, so it's always good to explain it in terms of examples. All right. Then you have chronological bias. Again, I have explained this with an example. So, you know how I said I have a PhD student who was looking at, say, type 1 diabetes and hemoglobin. Okay, so for instance, in this case, if you have, say, if she collects the HbA1c blood levels in December during Christmas time, it would be highly likely that the participants will have a high HbA1c level. Okay, because it's a feasting state. Okay, it's Christmas. Okay, so people are eating and they're having fun. All right. And in January, when comes the resolution, in January, people are so health conscious and they are like, oh no, now enough of these cookies and cakes. Let me get back to my healthy diet. And then you may be recording a lower HbA1c readings or the regular HbA1c reading. And therefore, you need to minimize these kind of chronological biases. Okay, so recruit participants in the same time frame, control for these factors. So basically, all of these kind of things, guys, needs to be taken into account when you're collecting data. Okay, so basically, we have told her to start collecting data, say from end of January. So both of the extremes are prevented. Say a big feasting state, a big fasting state. By end of January, early Feb, people are generally coming to their regular routine, and therefore your results are more likely to be reliable to what is generally seen, okay, in your sampled population. Then you have participants recall bias. Obviously, you can see this is very likely, especially in dietary studies like nutritional epidemiology, which I do, where you have, say, questionnaire data, like I have questionnaire data for my picky eating study, and participants may think that, oh, what did my child eat 7 days back, or say 24 hours back? And there could be, say, mistakes in this, okay? So in this case, what you do is, wherever possible, wherever applicable, you try to have some objective data source with your subjective data source. Okay, so you may have, say, with objective data source, you can have, say, HbA, your blood test. Okay, so for example, if my PhD student, if she is recording, say, the dietary data, okay, to see what are the types of carbohydrate rich food and what is the insulin regime of these individuals, and then she's correlating this with HbA1c level, this is a much more stronger data set, okay, because she has objective data, blood levels of HbA1c, alongside the dietary data and the more subjective data, which can have participant recall bias. All right. Then you have transfer bias, where you lose participants to follow up. And I gave you a few ideas as to how to do it. You need to engage your participants constantly. This could be, say, by a personalized email, personalized phone call, sending them a newsletter, depending upon what your research question and your theme is, contacting them in office hours, having home visits, or giving them, say, small, say, perks or benefit for free car park if you have to collect data in the university hospital, things like that. Okay, so this is called as, say, transfer bias. So you don't want to lose participants to, say, drop out and follow-ups. All right. Then you have, oh, why is this twice? Hang on. So I did the Hawthorne one. I did chronological biases. Oh, okay, my bad. I've just written chronological biases again over here, which I shouldn't have. But it's okay. All right, I'll remove that out for you. So this is again data collection stage 1, where you have exposure misclassification. Okay, so what does exposure misclassification mean? For instance, if I take a food frequency questionnaire, which is only capturing intake of fruits and vegetables, all right, I cannot generalize this data for all 5 food groups. So for instance, you have 5 food groups such as fruits, vegetables, then you have your dairy, then you have your protein rich, okay, and then you have carbohydrate rich, okay, your cereals and stuff like that, all right. So if I'm collecting data on fruit and vegetable, my results are only for fruit and vegetable. I cannot say that because the participants are having low fruits and vegetables, they are also not having, say, multigrain cereals, and they are also not having lean protein. No, how can you make this judgment when your data which you have collected is only for fruit and vegetable? Okay, so exposure misclassification. You cannot just overgeneralize your result. Therefore, you need to have very, very clear study objectives, and you need to be clear of what you are collecting. All right. And avoid using proxies of exposure, use validated measures. So basically, guys, what this means is that, for instance, when we look at dietary data, okay, so in dietary data, you have, sometimes you need to acknowledge proxy indicators, all right. So for instance, you have weighed food record, meaning you're weighing all food that your participant is eating. You're calculating the plate waste, you know, the food which they haven't eaten at the end. You're calculating what food they ate and all of that. So that's a gold standard of measurement. But you cannot do that for every research. You can't do a weight food measurement when you have a sample size like myself, like, you know, 400 people. All right, then what do? Then you use proxy indicators, such as you have a food frequency questionnaire, which is quick to complete. All right, so now when I'm using proxy indicators, in this case, I cannot avoid it. Okay, I've written over here, avoid using proxies. All right, but you cannot always avoid it. So yes, I have taken dietary data, and I'll be acknowledging that yes, my dietary data is using food frequency questionnaire, which has its own limitations. All right, now in the other end, proxy could be, in terms of exposure, could be, so exposure over here is, say, my dietary data. Okay, now I want to see, for example, what is the impact of dietary data on weight status. Okay, so over here, for instance, the proxy indicator for weight status could be BMI. All right, so with 400 people, the majority which I can request them to do is height and weight and calculate their BMI. Okay, now I know for the outcome BMI, the gold standard could be, say, doing DEXA. Okay, dual X-ray absorptiometry, which is the big tool which you use for, say, calculating the body fat and the lean fat composition of an individual. But I'm using a proxy indicator, which is height and weight and BMI, because that's the only practical thing feasible. So where you can avoid, you avoid. Where you cannot avoid, you have to acknowledge. Okay, you just have to minimize it. So the other way of minimization in terms of my outcome could be that I calculate their, say, body weight as BMI, and I do their waist circumference, meaning I have some reliability. If both of them are showing the same pattern, the waist circumference and the BMI and its association with that dietary data, meaning I have some sort of credibility to my findings, because both outcome variables are telling me the same sort of a story. Okay. Similarly, if I ask them to do a food frequency questionnaire, and I do their, say, if I do a part of the sample, I do 24-hour dietary recall, then I have some sort of credibility in showing that, look, food frequency questionnaire also gave me the same finding, and 24-hour dietary recall also gave me the same finding. Okay, so this is how you try to avoid or you minimize these sort of exposure misclassification. Okay. So yes, exposure and outcome misclassification, both of them I explained to you. All right, so I hope it makes sense, guys. So basically, where you cannot avoid, you try to minimize. How do you minimize? You try to take two methods which can give you robust finding. Okay, so you have more confidence in your finding. Okay, so two weak methods together become a bit more stronger than just one weak method, in simple terms. Okay. All right, guys, then you have performance bias. So what is performance bias? Where, for example, this is again data collection stage, where the participant or the researcher knows that where they are allocated. Okay, so the best way around this is a double blind randomized control trial. Okay, and a cluster randomized control trial as well. So I have explained you what a cluster randomized control trial means. Look at your week 2 lectures. All right. Okay. Then you have biases at the evaluation stage. So for example, you have analysis bias. So what is analysis bias? For example, you have you are only reporting significant findings which you found and not the non-significant findings. Guys, the first thing what my PhD supervisor taught me was, she's amazing, she taught me a lot of things, and I know I'll be teaching you, I'll be giving you that the philosophies throughout my throughout these 13 weeks that you are there with me. But one of the very important thing that she taught me was, a non-significant result is in a result itself. Okay, why is a non-significant result a result in itself? Because you are helping the other researchers to know that, look, if you're going to go this way, you're going to get non-significant result, so you might as well investigate some other variables which could be related to the outcome. Does that make sense? Okay, now this depends upon your research question, but it was very applicable in my research question for my PhD. Okay, so yes, that is something. The other way of you where you have analysis bias is where your, for example, your study is pharmaceutical funded, and they only want to say report good things about their pharmaceutical product. So they stop you from reporting things if their pharmaceutical drug is doing bad. Okay, so they are like, no, you're not going to publish this. We are funding your research, so no way. All right. So what is the way around this? So guys, these 2 points are actually together. Okay, citation or publication bias is something like this as well, where you're publishing significant results only and not and you're say avoiding non-significant results. And again, if your say your study is industry funded or XYZ funded, and they only want to show good things about their product or their method, so then they'll ask you to not say report their non-significant finding. Okay, so what is the best way around it is, yes, you have to report results ethically first. As a researcher, you have to be ethical, and very, very important is these kind of things should be discussed and clarified during your negotiation stage, where you are developing your study design, where you're developing your project idea with external collaborators and stakeholders. You sign a memorandum of understanding or intellectual property agreement, a collaborative agreement, research collaborative agreement. These all things, paperwork should be done and clarified. Therefore, then you become confident, and even if you have say results which do not make the pharmaceutical company happy, you have evidence, you have signatures behind you to advocate and to tell them that, look, we are going to publish this because we have signed a contract saying that irrespective of the final result, whatever it is, we have to say, we have to be transparent for the public and for the wider fraternity. All right, so that is basically called as analysis or citation bias, and that is how you would be potentially addressing it. All right, okay. So guys, that's the end of the lecture, your week 4 lecture, and I'll see you in your next lecture.